Okay, good afternoon, everybody. Okay, first of all, I am extremely thankful to organizers for giving me this opportunity of presentation. At the same time, I am grateful to my collaborators, scholars, and colleagues for inspiring me to present before you. So accordingly, the title of my presentation is Solar Plasmas, Equilibria and Fluctuations. This is our Tezpur University, a short glimpse. So layout of my presentation is very simple, standard. So it bridges basics to applications. So first of all, sun is defined and explained or interpreted differently in different spheres. But for plasma physicists, we treat plasma, we observe the plasma express of sun. So accordingly, the sun is redefined as a huge plasma fireball formed due to gravitational collapse dynamics. So accordingly, there are standard solar models proposed by Ian Parker. So in the standard solar model, what is there? So spherical symmetry is considered, and your neutral gas approximation is there, and hydrostatic equilibrium. So spherical symmetry, by that I mean the angular parts, that is your polar and azimuthal degrees of freedom are not considered, only the radial dependency of relevant physical variables are considered. So accordingly, the energy generation and composition in plasma in the sun is your composition hydrogen in most, and then helium, then minor amount nitrogen and oxygen. And as you know, the energy generation process is thermonuclear fusion reactions, converting your hydrogen into helium together with release of tremendous amount of energy on the order of 26 MeV. Okay, so the governing equations in the standard solar model are your gas, the ideal gas equation, that is equation of state, force balance equation, then energy balance equation, and this is your mass conservation equation of continuity. Okay, standard solar model gives the properties of sun as given here. These are the fundamental properties: age, mass, radius, etc., luminosity, etc. These are textbook things available in basic books. Okay, so the equilibrium patterns as per my title. So to understand that, so gravity electrostatic sheath model was proposed in 2007, which was published in APJ. Okay, so according to that model, so the main motivation of the model was the existing Parker's model or neutral gas model, because the connectivity between the interior and the exterior through plasma collective effects was not coined. Then emission mechanism of solar wind plasma, it was also not there. Then precise definition of solar surface boundary, it was also not there. So it motivated us to propose this theory, and this neutral gas approximation has been relaxed with the plasma degrees of freedom. Then SSB is redefined by maximization of solar cell gravity. So here, another important point is that from the fundamental physics of electrodynamics, we know that find out the potential field, associated diagram, pictorial profiles. So here we find that at the surface, the field profiles, the potential profiles behave extremely, that is maximum. So conversely, we can utilize the same fundamental physics in order to relocate or identify the solar surface boundary. So that was done in that model, and what boundary we are considering here is that the composition of our plasma, what we consider two-component plasma, electron and hydrogen, proton, and your thermal, your gravitothermal coupling coefficients of your electron ions are computed, estimated here. So here we can find that for electrons, being the lightest species, so it has the coupling parameter more. Okay, in case of your ion, it is less. That is, gravity is working more on the ions, but least on the electrons because of their tiny inertial mass. So because of that, what happens? And because of electron mobility, charge separation takes place, and this is what causes sheath formation. Okay, so accordingly, we define our solar plasma variables. So these are radial position normalized with respect to Jeans scale length, then Mach number with respect to sound phase speed, then your potential with respect to electron thermal potential, then your gravitational potential with respect to your CS square, which is also called the kinetic acoustic potential. Then accordingly, the temperature factor is introduced, and with this, these are the equilibrium equations for characterizing the equilibrium structure, steady structure of the sun. So this is your Boltzmann distribution function or distribution equation, and this is causality condition, this is momentum equation, this is continuity equation, and the coupling equation is your gravitational Poisson equation. And here we can see the 2 by xi. This term is coming only because of the consideration of geometrical curvature effects, that is deviation from plane geometry. And these equations are utilized to find out one condition for bounded solution to exist. Before directly proceeding to numerical solutions, we are just testing whether it is possible. Then by applying your extremization condition, we found out that there is a condition existing in terms of escape velocity, that it must be the velocity of the solar wind particles to escape the defined solar surface boundary. So this is just equivalent to your Bohm condition for plasma sheath formation. So as you know, whenever plasma is in boundary or in contact with some boundary, a plasma sheath is formed, which is your non-neutral space charge layer. And the condition states that the ions moving towards the sheath entrance point must be at least supersonic. So this is the case. Okay, so these equations are for the outer scale, that is solar wind plasma dynamics. Again, all the equations are written except that your gravity is now replaced, cell gravity is replaced with your external gravity, and Poisson equation of your gravitational matter distribution becomes redundant. So that is excluded. Okay, so now the complete set of equations are solved numerically as an initial value problem. So how to get the initial values then? We don't have the initial values, what inputs we should get? So we have applied stability analysis, nonlinear stability analysis in order to find out the input values, the initial values. And accordingly, we simulated it as a complete closed set of equations, coupled set. So here you can see this is your gravity maximization, and this is your corresponding electric field strength. And we find that at a position 3.5, so although it is visible, it is your 3.5 on the Jeans scale length, there is a perfect balancing. So immediately we conjecture that this is the location of solar surface boundary, because there it becomes maximization. At the same time, it is gravito-electrostatically balanced. And these are the associated your electric potential profiles, and these are the Mach profiles. Because cell gravity is strong in the interior side towards the heliocenter, that's why Mach number is very small, but after that it becomes uniform. And for further reconfirmation that whether the surface is perfectly your gravity-electrostatically balanced, we have found out the net gravity-electrostatic force, and accordingly the profile shows that at the surface boundary 3.5, it is exactly 0. That is, exact gravity-electrostatic force balancing has been done, and accordingly the surface is located at your 3.5. Okay, so next is your on the unbounded scale also we have found out the Mach profiles. These profiles are you see. So there is a transonic point. After that subsonic solar wind becomes via transonic to supersonic domain. And these are the associated your potential profiles. And this is the just zoom version of this. Here you can find this is the transonic line, that Mach equal to 1, close to 1. Then here we find many intermittencies. So after that it becomes supersonic, like that supersonic, hypersonic. Okay? So whenever subsonic to supersonic is there, in between there is a transonic point. And this is required for even your plasma sheath modeling. That's why the transonic zone of plasma was coined, transonic plasma. Okay, fine. So the outcomes of the GS model is that various properties have been redefined, and as per we know that on this scale, two-scale theory of plasma system, so like in your standard model, there are so many concentric layers, but in this case only two layers, only two system is considered, subsystem. One is your solar interior plasma, and other one is your solar wind plasma. So here we can find that out of this analysis, we found various properties that two types of sheets are there. Then your surface is located at 3.5. Then SSB draws high negative current because of electrons, that is electron-dominated current. And other parametric estimations are there. And these are quite in conformity with standard solar model as well. And we have also compared this model with the existing standard solar model. And these are the various properties what we found. that out of main important point is that here the laboratory plasma physics, sheath formation physics, that has been coined in our model, and here plasma fluid is considered, and equilibrium in the earlier cases, it was only hydrostatic, but here it is hydrodynamic equilibrium, and inhomogeneities have been considered, okay, and so forth. And the most important point, the acceleration mechanism, according to a standard solar model or Parker model, it is your D-level nozzle effect. But in our case, it is your GS force action. Okay, so we have also applied your copper distribution modified polytropic model to find out this, and the results, of course, we got very new results, and which also confirm with your other missions, including some of the case of PSP. Now the fluctuation dynamics. Once the equilibrium is done, we have defined the equilibrium. Now around that equilibrium, we are doing the fluctuation analysis. So first we do just what is the motivation? Motivation is your heliosysmology motivation. Okay, so 5-minute solar surface oscillations, and conventionally in your standard solar model, P mode, F mode, G mode are there. And out of that, P mode, everybody knows this is acoustic in origin, and G mode is gravitational in origin, and F mode is your surface mode, which is buoyancy driven mode. And what is the need? Because structurization or the identification of the morphological dynamics or understanding interior of the sun, these are done only with the help of your in situ measurements founded on heliosysmology or heliosysmic modes. Because these are high temperature, so that's why direct measurements is not possible. But for example, if for this F mode, if the F mode is frequency is known, then by that it is surface mode, so the radius of curvature can be understood with this. It can be estimated. Okay, so our motivation is here, so gravity electrostatic sheath fluctuation is done, and here instead of already gravitating plasmas or self-gravitating plasmas are highly inhomogeneous in nature. So equilibrium is inhomogeneous and non-uniform. Therefore, local analysis is both improper and inadequate. So because of that, we applied a different formalism. So accordingly, the model consists of two fluid hydrodynamic field-free equilibrium plasma on Jeans scales. Then global quasi-neutrality with spherical symmetries is still retained, and special inhomogeneities, that is lowest order gradient effects even on the equilibrium are considered, and spatiotemporal inhomogeneity and fluctuation parameters are also retained. So bounded scale formalism for the SIP, these are the governing equations. Let me tell you that these are the same equations as before, but only difference is that the temporal evolutionary terms are retained. Because in earlier case, it was just stationary equilibrium characterization. Okay, and why we have considered field-free? Because there is one paper that for pure characterization of the modes or heliosysmic modes, we should consider always field-free plasma. Only then pure characteristics can be evolved. And it is, of course, a first step from our group. Okay, so this analysis is done this way. Here, all the equilibrium parameters of relevance are functions of position. Okay, and these are the linear fluctuations, and after that, linearized equations are coming out of this form. These are the same equations: continuity equation, momentum equation, and gravitational Poisson equation in part of form. Okay, now the perturbations evolve in this form. Okay, we assume this. Okay, and here one important point is that still it is a spherical geometry, but we have done plane wave analysis here. So under the condition that your Kj is much greater than 1. Okay. So these are all the coefficients, equations, and finally we got the non-local dispersion relation. Okay, for SIP description or for the characterizing or analyzing the SIP fluctuations, and the dispersion relation comes out to be of this form. Here we can find that the dispersion appears in a space, in a space, Fourier space defined by k and omega. In addition to that, some coordination geometrical gradient effects are also appearing because of non-locality effects, because of lowest order gradient effects, equilibrium gradient effects. Now if we consider purely homogeneous plasma and under plane geometry approximation, this equation gives this result. And this is well standard, well known equation that this is your, and it is on Jeans scales, right? So therefore, it becomes nothing but your Jeans mode dispersion relation. So this is the linear dispersion relation for the Jeans mode. It is quite well known, matching with previously reported works. Okay, now unbounded scale analysis, HWP scale, again the same equations, but only difference is that the gravitational Poisson equation is redundant. So rest of the things are as before. So amplitude or eigen function equations are given this way, all these forms, and the corresponding linear dispersion relation for your HWB fluctuations are given in this form. Again, what we find, local effects are appearing in the form of your omega k, and non-local effects or equilibrium inhomogeneity effects are appearing in the form of diverse equilibrium gradients. Okay. Once again, for instant reliability checkup, we apply the plane geometry approximation in homogeneous equilibrium. Okay. And finally, we get this equation. And this is, everybody knows, this is purely acoustic mode. And acoustic mode. Okay. Now the effects of geometrical curvature and other realistic effects on the fluctuation dynamics. And this is also done already, and we find similar things. But question is that here the phase velocity of the modes on both the scales are functions of your non-thermality index. Okay. Now these are your graphical profiles, and here we can find that on this up to this scale, here there is no variation of the real part of the frequency. Okay. So you see, for your spring mass system, we consider spring, for example, you consider this as a mass and this is spring. So it is oscillating this way. What is the frequency expression? This is omega equal to root over k by m, ks by m. Okay? And ks is your spring constant. There is no k dependency. Therefore, on your k space, that is your propagation vector space or angular wave number space, there is no variation. So that characterizes that it is oscillation. So this is up to this is oscillation. After that, it becomes proprietary in nature. Okay? And on this again, a little bit nonlinear effects are appearing on position as well. And these are the corresponding growth behaviors. So these are stable oscillations, okay? And from there, we get stable oscillations, okay? And on your, especially radial distance, there are some nonlinearity effects are also found. So question is that here what we find? We find one is your propagatory characteristics, and second one is non-propagatory but oscillatory characteristics of the same. Now, this is a detailed analysis of the same on Zoom version. So up to this oscillation, then this is again propagatory nature, and these are the corresponding your 2D profiles fixing your position. Here we can find that from up to here, there is pure G's mode is found here in between, then purely acoustic mode here, and purely GS mode, which is your oscillatory mode here. So immediately it conjectures that there are three types of distinct types of mode. One is your oscillatory, okay, and two are propagatory, okay. So then again, from there, we also found out the time period. So here in time period, we find that at surface, it is your just, you see, so 5-minute oscillation, 3 to 5 minute oscillations are also found here. Okay, then these are the corresponding amplitude equations, and since it is gravity-electrostatic case, and here again, these find that these are in opposite in phase, in accordance with previous equations. Okay, these are again the same fluctuation of your amplitudes. And once again, we find that what is the position or what is the corresponding behaviors near the surface. And this is again in conjugation with the previous cases. Okay, so these are real frequency and imaginary frequency on the unbounded scale. Here again, we find that it is purely acoustic mode. Okay, there is no oscillatory part, therefore it is propagatory mode. And here again, so correspondingly stability, these are highly stable. P modes are highly stable in nature. Okay, so these are same, so period of oscillations from the same frequency. Here we find that up to this, here again, so 10-minute oscillations are found. Okay, 10 minutes. Okay, so here again, the normalized electrostatic potential fluctuations we have found. These are again in accordance with your conjugation, mutual conjugation with each other, so that the surface remains finite, again turbulent, of course. Okay, so these are again the profiles with thermality effects. And here again, we find the propagation speeds. Okay, so that's why whenever it becomes propagatory, it becomes dispersive on the Jeans scale, but non-dispersive on the your unbounded scale. Okay, anyway, so these are the similar profiles we found out on the unbounded scale, unlike the previous bounded scale. So in totality, just my conclusion is simple. Our conclusion, so 3 types of distinct modes are analyzed with the help of this spectral analysis, linear dispersion analysis, okay? So these are your GS oscillator with this propagation and your time period characteristics, then GS wave, again with this your time period and propagation characteristics, and this is electrostatic wave or P mode, which is with these characteristics, okay? And of course, non-thermality factors, if consider, they also energize or accelerate the modes. Okay, so these are some references of the same, and our works, different works are also done in the presence of different conditions. And here again, negative ion effects, these are also considered, and it sinks down, sinks in because of the consideration of negative ions. Because negative ions are there even in your galactic sources, extragalactic sources. And one more, we also modified that. Already we found some singular type of structures at the core. So that's why the gravity, Newtonian gravity is not sufficient to explain this. So we applied a modified gravity with non-locality corrections arising because of diversified equilibrium inequalities, and this work also published in PRE. Then one more, this is also one we done with the help of your bispectral thermostatistical analysis. This work just yesterday got published in APJ. Okay, and these are some reports. We are thankful to media persons for publishing our release notes on research. Okay. Okay, thank you very much for your kind attention.
Thank you, Professor Karmakar, for showcasing the research that you have been doing. The floor is open for questions. Students? Okay, while the students are thinking, maybe I can ask you. So in what I didn't understand is in your models, initial models for the solar, the sun, do you actually also account for rotation? Because we know that the sun is differentially rotating.
Yeah.
But you are essentially doing 1D calculation, right?
1D simplified calculation, idealistic calculation,
okay,
no rotation, no magnetic field.
Do you think how rotation, I mean, according to you, how rotation will play a role? Differential rotation will play a role in terms of your two plasma system where you have this gravitationally bound sun and then the solar wind. So how do you think the rotation will play a role there?
If rotation is incorporated, it should be incorporated through a Coriolis force in the momentum equation. And because of that rotation, what will happen? It will act, you see, so whenever it rotates, another force comes, right? Centripetal force, and it comes only because of your velocity counterpart, right? mv square by r for an orbiting body. So it will give extra stability against cell gravity, because sun is a product out of cell gravitational or gravitational instability, and sun remains cell gravitating even after formation. That is till your white dwarf stage. Still then it is cell gravitating, it remains. That's why it is giving additional stability towards. So not other modes, but G mode is going to be highly affected because of that. So frequency or energy, it is going to be reduced if considered. But it will be our, thank you, very nice question. It will add to our work. We may do the next continued extension. Yeah, thanks a lot.
Great. Any further questions from anyone?
So hello, excellent talk, sir. And I just wanted to know that, like you said, the gravity will be corrected, the non-locality. For that, you still will be doing 1D model, or it will be more than 1D then? Because, I mean, finally you have to do something like tensorial and all these things if you want to do this.
Here, yeah, very nice question. Here, throughout the analysis, ignored the radial angular counterparts. That is your polar parts and your azimuthal degrees of freedom. So these are all radial directions, which may be considered as, again, 1D. Right. So it is 1D model. And even though that I told you that non-locality corrections, it could be incorporated through other dimensions as well, including all the your angular degrees of freedom, polar and azimuthal. But we didn't do. Things are going to be complicated and more realistic, of course.
Yes. Okay. Thank you very much.
Let's thank Professor Karmakar for a very nice talk. Thank you.